Yeah, Shishwan is up. It's ready for you.
Okay. Very welcome, everyone. So today I'm going to talk about chapter 5 of the book, and the name of the chapter is Box-Jenkins ARIMA Models. And my name is Sixuan Wang. I'm going to try a little bit of fancy things here. So that's my name. And I'm a lecturer in economics at the University of Reading. So many people found that my name, Sixuan, is very difficult to pronounce in English. However, I would like to point out that that is not the case. So the pronunciation of Sixuan is very similar to Sichuan, if you know the Chinese spicy food. Okay, so during this presentation, I'm going to combine three things. So I will talk about what is in the book. I think the book is mainly for practitioners. I think I read the book. It's very easy to follow, and it has the example mainly based on the cells. And even for the equation, it's written directly with cells. But I come from econometric and statistical background. So I will add my own reflection on the book chapters on each of the topics. So I will not only talk about the book itself, I will also add my reflections. But my reflections may be a little bit technical. And the last thing is that I would like to show R demos, some simulations directly in RStudio. So I already prepared my code, and we will go to my code intermittently. And so let us get started. So here's the outline of the chapter. There are 7 topics, sections. So the first one is about stationarity. So in the book, it is defined in this way. So stationarity is kind of stationary time series, which are, so it uses cells directly. It uses a cells history that has an underlying structure that does not change over time. So the definition here is intuitive, but it's a little bit vague. So how do you define something does not change over time? And I will add my reflection in my lecture slides, but this is the general definition. It's very easy to understand. The idea is that the nature of this time series stays the same over time. And the book provides assessment on stationarity. So basically speaking, you look at the plot of the time series, then you have a rough idea or initial idea whether this time series is stationary or not. So this is my reflection. So in my I'm also teaching this ARIMA model at my university. So but we teach it in a little bit technical way. So this is our definition. So for weak stationarity, you need to have 3 conditions. So what are not changed over time? First of all, the mean of this variable stays the same. So if you have a trend, then the mean is not the same. So this will not satisfy. The second one is the variance of this variable stays the same. As you can see, the variance at the time t, at time t minus 1, even at time 1, they stays the same. So if you have something, let me say, so have little bit variation at the beginning, then start to have large variations. So this is also not stationary. So the last thing, and I think this is not talked about in the book, is the autocovariance only depends on the lag k, not on time t. So if you look at the covariance between the variable at different time points, so the first one is the variable at time point 1, and then the variable at 1 plus k. So if you look at the gap between them, the gap is k. The second pairs, 2 and 2 plus k, the time difference or the lag is also k. The last pair is also k. So this is autocovariance, and it stays the same for any k, any lag. So k can be 1, can be 2, can be 3, can be any integers. So that's the 3 criteria. And I think it provides a little bit more, how can I say, rigorous way how you define the underlying structure that does not change over time. So basically speaking, 3 things: the mean, the variance, and the autocovariance structure does not change. So this is one version of stationarity. It is called weakly stationarity. Some people also call it the covariance stationary, or some people also call it the second moment stationary. And there is another version of stationarity. It is called stationarity. I'm not going to the details, so this is for your information. So there is another version as well, but this weak stationarity is the most well-used version. Okay, so the chapter said that, okay, you can look at the graph to gain an initial idea. As far as I know, there are several statistical tests on stationarity or on unit root, so that it can give you rigorous way to assess whether a time series is stationary or not. So the first type of the test is called the unit root test, and the most popular 2 tests are ADF tests and the PP tests. So the thing is that the long hypothesis of those 2 tests is that there is a unit root. So by unit root, it means non-stationary. So if you reject this non-hypothesis, you end up with stationary series. And for another type of the test, this is named as a stationarity test. The non-hypothesis is that, okay, this time series is stationary. So if you do not reject this non-hypothesis, you end up with stationary series. So those are the most widely used tests to assess stationarity. Okay, so we talked a theoretical part, and then let us look at some demonstrations in R. So I'm going to simulate the simplest stationary process. This is called the white noise process. So can you see my R studio?
Yes, yes, I can.
Fantastic. Okay, so I already provided code here. So as you can see, I generate the white noise by this command. Then I plot it. So as you can see in the graph here, the mean stays the same. The variance, the fluctuation range also stays the same. And you cannot see it easily, but I can show you later. The autocovariance structure also stays the same. And you can plot the histogram. And also, more importantly, you can plot the autocorrelation function. In short, that is named as ACF. So for the ACF, at lag 0 is always 1. Because this is white noise does not have any autocorrelation. So all autocorrelations are 0. So that's why I say the autocorrelation structure is the same. So as you can see, the empirical ACF from this simulated data stays within the insignificant range. So this is a stationary process. And then let us look at deterministic trend process. Basically speaking, you add a trend to the white noise. So I generate trend, the noise, then I make them together. So that's data X is my deterministic trend process. You plot it. So that's the deterministic trend process. As you can see, of course, the mean does not stay the same. The mean at each time point is increasingly in a deterministic way. So this violates the stationary condition. The first one, the mean is not the same. And also you can plot the ACF, as you can see. The non-stationary process usually have one feature, that the ACF decaying very slowly. So this is roughly the idea here. Okay, so this is one non-stationary process. Also, let us look at another thing. So this is the violation of constant mean. Let us look at another example, violation in constant variance. So I'm going to generate a process that has a relative small variance in the first half, and then relative larger variance in the second half. And I'm not going to generate, let me just generate just one trajectory. And then you will see it. So before 50, the variance standard deviation is 1. After 50, the standard deviation is 2. But it's very hard to judge, okay, whether this is a real volatility change. So I'm going to increase the number of simulation, then plot it. Now you can see, okay, there are 5 trajectories here. After time point 50, it really have larger standard deviation. So you can also increase to 100 trajectories. Then it will give you much better idea. Yeah, so as you can see, after the change in 50, the variance doubled. So I provide all the R code here, so you can try it by yourself. And I also provide the notation here. So deterministic trend process, and also the structure break in the variance. That's the R code. Okay, that's the concept of stationarity. So let us talk one of the most widely used process, and that is a stationary process, autoregressive model. And in short, that is AR model. So in the book, it just used the rotation cells. And so this is the AR1 process. So as you can see, on the left-hand side, you have the variable at the time point t. On the right-hand side, you have a constant, you have a coefficient, and this coefficient is multiplied by the variable, the sales data in the previous period. How do you know that's previous period? Because the subscript is t-1 here. And do not forget that you have the random noise. So because you only include one leg of the variable, that's why we call it AR1. So if you include not only previous period data, you include the data in the previous, so 2 periods ago, together on right-hand side. So we call it AR2 process. So in the same way, you can include 3 periods, 4 periods. So you end up with AR3, AR4, etc. So one thing we need to pay great attention is the ACF and the PACF. So ACF is autocorrelation function. PACF is partial autocorrelation function. And for these autoregressive models, they have the pattern, okay? So theoretically speaking, you can prove it. And we are not going to do the proof here. This is the conclusion. For the AR model, the ACF is geometrically decaying. How do you, what do we mean by geometrically decaying? So this is the lag. Let me say this is K, and this is the ACF. So it looks in this way. So this is geometric decaying. For the PACF, so it will truncate it at P. So P is the order of the autoregressive model. So let us say if P is 2, it will look like this. So at lag 1, there is a value. At lag 2, there will be a value. At lag 3, theoretically speaking, it goes to 0. And so on and so forth. So you only have those 2 spikes in the PACF for the autoregressive models. Okay, so let us do some simulations, see whether this is the case. So we go to RStudio, and by this command, I generate 1000 trajectory of AR1 model, and the coefficient is 0.5. So I plot it. So this is autoregressive 1 process by simulation. Then let us plot the ACF. So as you can see, so at lag 0, it is always 1. And then it starts to geometrically decay. At lag 1 is about 0.5. There are some simulation errors, but about 0.5. Then is 0.25. Then is 0.125, etc. Every time you multiply by half. So this is what I mean by geometrical decay. And then
can I just say something about?
Sure.
So I mean there are because Sichuan is using base R here, but like there are packages actually that ignore this autocorrelation at lag 0 because it's not really helpful and sometimes it's confusing. So you can also ignore it. So that if you see that 0, just ignore it because it's not helpful and it is not it's confusing. And like more if you use forecast package or you use Fable, so they have functions. If you use ACF, then you don't see this lag 0 there. Just wanted to clarify that.
Yeah, thank you. So that's very helpful. So yeah, there are some better packages, so that it has a more intuitive presentation on the graph. So I'm just using the basic R, but I just want to show you the idea here. And then for the PACF, okay, so in this case, because it's AR1 model, so it will truncate. It will should have only 1 spike. So here for the PACF, if you look at it carefully, the lag at 0 is ignored, and then this is lag 1. Yep. So for the lag 1, you have the spike. After it, it's all in the insignificant range. So basically speaking, it is consistent with what I show here. If it is AR1, then you only see 1 spike. After that, it is truncated. So basically, theoretically speaking, they are 0, but you see a little bit very tiny spike here. That's simulation error. Okay, to reinforce the understanding, let us try AR2. So AR2 plotted, and then I plot the ACF. So as you can see, because I have a negative coefficient, so it's going up going up and going down by 10. So, but if you look at the magnitude, it is still geometrically decaying.
And there's another question: is this the point?
And for the PACF, so as you can see, for the leg 1, you have some significant PACF. For the leg 2, you have some significant PACF. After that, it is truncated. Basically, they are not significant anymore.
No, just double check because sometimes.
Sorry, there are some background noise. My partner is also working, and we are only working in the same room. So let me continue. So the next thing is the moving average model. So here is what in the book. So this should be MA1, MA2. So previously you have the previous cells on the right-hand side, but now for the moving average model, we don't have that. So instead, we have the error in the last period. So this epsilon t-1 denotes the noise in the last period. So if you only have one previous noise, that's MA1 model. If you have the noise at last period and also 2 periods ago, that is MA2.
Yeah, it's a new question under this question this year.
And also, importantly, we have the pattern for the ACF and the PACF for the MA model. Basically, you swap what you see in the AR model. So now, I will say the PACF first. For the PACF of moving average process, it has the pattern geometrically decaying. For the ACF of the MA model, it has the pattern of truncation. Okay.
Oh, check it online. I think Huawei is not listed in China.
So to better show you the pattern, I think we can also go to the RStudio to do some simulations. So I'm simulate this MA process, MA1, and then I plot it. And this is the ACF, as I mentioned. So it has a truncation pattern. So this is like 0, it is 1, you can ignore it because it only have one order. So you only have one spike in the ACF. For the PACF, so it's going up and down, but if you only focus on the magnitude, so it is geometrically decaying. So that is the pattern for MA1. So let us look at the MA2. So I simulate MA2, I plot it, and then the ACF.
I will do the sentinel procedures here. Is that right?
The ACF should have a truncation
I will do the sentinel
at order 2, but the order 2 is very small. I think this is simulation error, so I'm going to increase the MA2 coefficient. At the same time, I'm going to increase the simulation application numbers, and then it should show better idea. Yeah, this is much clearer. So it has the truncation pattern. What's the order of MA here? 2. So you only see 2 spikes, ignore the 0 there. For the PACF of MA2, it should have geometric decaying pattern. Yes, so if you only look at the magnitude of PACF, it is geometrically decaying. Okay, so let us look at the AMA model. So basically speaking, the ARMA model is the combination of AR model and the MA model. So for on the right hand side, you have the AR part. Also, you have the noise from the previous period. You have the MA part. Because I only include one leg of the variable and one leg of the noise. So that is AR, MA11 process. So the first one, we usually name it as P. That's the order of the AR part. The second number denotes the order of the MA part. So usually we use lowercase q. Here's a pattern for the ACF and the PACF of the ARMA model. So now it becomes complicated. So both of the ACF and the PACF are geometrically decaying. So there is no truncation anymore. So let us look at the simulation here. So I simulate ARMA11 model, and that is the time series plot. Then I plot the ACF. See, is geometrically decaying. And for the PACF, if you look at the magnitude, it's also geometrically decaying. If it is not clear, I can increase the coefficient and also the number of simulation to make it more clear. So yeah, this is now much more clear. It is geometrically decaying if you only look at the magnitude. So let me make a summarize. So for the AR model and the ARMA model, the ACF is geometrically decaying. For ARMA model and the MA model, the PACF are geometrically decaying. However, the PACF of AR has the truncation. The ACF of MA model has the truncation. So that's how we will use to select the model by looking at the ACF and the PACF later. So now we can have the example. So in the book, it used sales data. However, I don't have that data. So I use my own data, which is public available. And I will do the fitting. I will do the model diagnostics. So, and very importantly, I will also do the model selection. So here's the data I'm using. I'm using the growth rate of GDP in the UK. And it is seasonal adjusted. It is quarterly data. And it is from 1955 quarter 2 to 2018 quarter 3. And the original GDP is in the million, but I converted it into the growth rate. And that's the website, you can download it. So it's about more than half century data. So it's a very long time series. So I'm going to show you the original data in RStudio. Yeah, some packaging. Then I have the data in my Excel. I input the data. I get the year. Do a little bit of, I truncate the first year because when you do the calculation for the growth rate, you lose the first observation. You have the GDP, you have the log of the GDP, you have the growth rate. So the growth rate is, so you have GDP. The growth rate is equal to log GDP at the time t minus log GDP at t minus 1. So that's how I do the calculation for growth rate. So let us look at the data. This is the original GDP. So as you can see, in 2008, we have the recession. Okay, my data does not have 2020 data. If we have 2020 data, we also have the recession now. And then I plot the growth rate. So this is the growth rate. As you can see, the GDP is non-stationary, so you cannot directly use ARMA model. And for the growth rate, it looks like a stationary process. And we can use ARMA to model it. And this is the histogram of the GDP growth rate. As you can see, we have the recession on the left, and sometimes we have a very good economy on the right. And let us look at the ACF of the growth rate. So it looks like this. So you can have a guess, okay, what you want to use by looking at the ACF, at the same time looking at the PACF. I'm showing you now. Yeah, that's the PACF. So here's the thing. How do I decide which model I need to use? Should I use AR? Should I use MA? Or should I use ARMA? And that's the pattern I just reviewed. So AR has a geometrically decaying ACF, MA has a truncation ACF, ARMA has a geometrically decaying ACF. For the PACF, AR and MA has the opposite pattern. And for the ARMA, it has geometrically decaying PACF. So by looking at those ACF and the PACF, if I will judgment by myself, I look at it. So the first three are probably significant. But is it really geometrically decaying? I cannot tell. For the second one, the first three, not the first one, at least the second one and the third one are significant. Is it geometrically decaying? I'm not 100% sure. So I personally find that if you just look at the PACF and the ACF, it's very difficult to make decision. But in the book, they choose MA1 because I think the pattern is much clearer. But for my data, I cannot tell. So what I usually do is I don't use ACF and PACF. I will use information criteria to do the model selection. And there are two most popular information criteria. The first one is AIC, the second one is BIC. And as you can see, they are calculated in this way. The first item is about logically likelihood. So if you have a good fitting of the data, the likelihood should be high. However, you have a minus sign here. So it will have more negative values. At the same time, the second item is about the number of parameters for AIC. So if you have more complex model, you will have a higher K. So basically speaking, it penalizes more complex models. The philosophy goes in this way. If you can have a simple model that works for this data, you shouldn't use more complex data. So that's the philosophy. For the BIC, it works in a similar way. It's just the penalization is slightly different. Instead of 2K, it's K times log of N. N is the sample size. Okay. And there are some comparison between AIC and the BIC. So BIC usually choose more simple model. And the AIC is not consistent. It usually picks slightly bigger model or complexer model. And this is the criteria. So which model is better? It should have smaller information criteria. If you see the information criteria are elective, you should choose more elective information criteria. So that's the deal. So that's the code. And so basically speaking, I will try ARMA 00, ARMA 10, ARMA 11, etc. So I will try all the way to ARMA 55. So how many models did I try? 36 models. Okay, and then I put them in a loop, and then I store the AIC in this container, and then I see which one has the smallest one. So I show you in the R code. So for the P-lex is from 0 to 5, for the Q-lex 0 to 5, and then you make your container. Then you have your double loop here. So it's running, it's trying all the combinations, 36 combinations. Yeah, there are some warning because some combination is not that good. But at the end of the day, what you need to focus is this table, the IC. And I use AIC, you can also use BIC. That's your personal choice. So this is the table of all possible AIC and AIC. And you choose the minimum one. So I have the code here. So the best P, that's AR order, is 3. The best Q, that's the MA order, is also 3. So that suggests to me the best model is ARMA 3.3. Okay. So I emphasize that yes, some people use ACF and the PACF to choose best model, but I just personally don't find it very straightforward. And sometimes it's a little bit difficult to make the judgment call. So I always use the information criteria, which is more, how can I say, decisive. Okay, after you do the model selection, very importantly, you need to do the model diagnostics. Maybe the best select model cannot pass some criteria. So what are the criteria here? What is the ideal situation? So first of all coefficients in your ARMA model should be statistically significant. And then the residual from your ARMA model should very close to the white noise, okay, without any autocorrelation. If there is any remaining significant autocorrelation in your residuals, so that is an indication you need to put additional AR or MA terms. So basically speaking, you need more complex models. So let us look at how my ARMA 3.3 model performing. So the first one is checking the coefficient. So I can show you in my RStudio. So that's the coefficient. So as you can see, those stars denotes the significance. So I have 6 terms, and I also have the intercept. So as you can see, most of them are significant with 3 stars, which means very significant. It's significant at 0.1%. There is only one which is still significant at 10%. Okay, so from this check, I can see all my coefficients are significant. Maybe MA1 is not that significant, but it is still significant at 10%. The second check recommended by the book is you overfit the model. You use a more complex model and see whether the coefficient become insignificant. And then I can show you their coefficients in my studio. So now, as you can see here, many terms they become insignificant because star here or even dot, which means they are not significant. This suggests that if you overfit, you end up with worse result. So the second checking criteria is also passed. The third criteria is let us check whether the residual are really white noise. So the first way is that you can look at the residual, but it's very hard to tell whether this is a white noise or not. Another more quantitative way is looking at the ACF of the residual. So I can show you. So this is the plot of the residual, and then this is the ACF of the residual. As you can see, there is no significant autocorrelation, which means my model is really good. ARMA 3.3. And there is a more rigorous test to check the residual is independent distributed or not. This is called the link book test. So as you can see, the null hypothesis is that the data, if you check it on your residual, then the residual under the null hypothesis are independently distributed. If you reject it, it means they are not independently distributed. So I'm not going to the quantitative details here. We can look at the results. So I show you in RStudio. So you need to specify the lag for the Linker-Bock test. That's not the lag for ACF, that's the lag for the Linker-Bock test. So what we need to focus on is the p-value, whether it is less than, let us say, 5%. And if it is less than 5%, you reject it. It is not independent disputed. That's not what you want to see. You want to see the p-value is higher than 5%. You cannot reject the null hypothesis, which suggests that the residual are independent disputed, which means this is very close to white noise. So I tried different lags. They are all more than 5%. So the third check is passed. The last thing in the book suggests that we also need to look at the residual, whether they are normally disputed or not. So you can do this by QQ plot, quantile to quantile plot, or use a statistical test that is called a Jake-Barrow test. But I think nowadays we don't need to check this assumption anymore. Because even for the ARMA model, we have the error term. Yeah, you of course can assume that's a normal distribution, but in many settings, I also used some ARMA model with the white noise with the error term follow other distributions like a T distribution with 5 degrees of freedom. So that's a heavy tail distribution. Also, you can use skew T distribution and even skewed normal distribution. And for those distributions, this model still holds. The estimation is still consistent. So I don't really see I don't think we need to check the normality anymore. But if you want to do the some kind of classical models with this kind of assumption, normality assumption, you can do it. But I personally, I just say personally, I don't think it's necessary. Okay, for the non-stationary time series, how should we deal with them? So the philosophy is that we convert non-stationary time series into stationary series by some tricks, okay? We convert it into stationary time series. How do you convert them? It depends on the nature of stationarity. So first of all, if you have the non-stationary in the mean, so for example, if you have the trend, I show you, so you can make a difference. So you simply model the difference between the cells. And if you make a one order difference, that's not enough. You can have the difference of the difference. That's the second difference, second order difference. And if your non-stationarity is in the variance, it's a little bit more complicated. Basically speaking, you need to convert the fluctuation at the different period into the same fluctuation across time. And the recommended way in the book is by Box-Cox power transformation. That's a formula. And this number is chosen by yourself, and some software can optimize it. So I haven't used this technique in my practice, so I'm not going to the details, but that's the recommended way. So what is the relationship between those ARMA and the ARIMA models? So forget about those details. So I think we can write in this way. So ARIMA PDQ, if this D is 0, you go to ARMA PQ. Okay, and then if this ARMA PQ, you got P is 0, so that's MAQ process. If this ARMA PQ, you got Q is 0, you have ARP process. So that's the relationship. Basically, ARIMA is the most general one. If you have you don't have the difference, you end up with ARMA PQ. If you only have the AR part, that's AR model. If you only have the MA part, that's the MA model. So the last thing is seasonal ARIMA model. So this is the most complicated model. Let us try whether I can explain it in a clear way to you. So now, if you look at the notation, this is getting very complicated. You have PDQ, that's for the ARIMA part. Now, additionally, you have capital letter P, D, Q as well, and you also have this small m. So the capital letter P is the number of seasonal autoregressive terms. Number D is the number of seasonal differences, and the number Q is the seasonal moving average terms. Number M is the number of periods per year. This is easy, okay? If it is quarterly data, M is 4. If it is monthly data, M is 12. This is easy. But how about those PDQs, capital letter PDQs? So I think I need to explain it by example. So if the first part is nothing, okay, there is no ARIMA part. Let us just look at the seasonal part. I only have one seasonal autoregressive term. So, and the frequency is 12. So this is what you end up with. On the left-hand side, you have xt. On the right-hand side, you have one seasonal autoregressive term. So that is xt minus 12. Everything stays the same. And now let us look at a slightly complicated case. You have ARIMA 1, 1, 0, which means you make one difference here. Additionally, you have seasonal MA part. Okay, so how do you do that? So imagine this is your original process. Yeah. Then you need to do the difference in the ARIMA part. So you end up with delta xt, which is xt minus 1. So that's delta xt. Okay, so you put the delta xt to the left-hand side, and there is no seasonal difference. So that's what you end up with. Okay, so that's constant, and you see there is a autoregressive 1. So you have this variable with autoregressive 1. So that corresponds to the 1 here. And you don't have MA part. However, you have the seasonal MA part, okay? And the M is 12. So you have the noise at time t minus 12. So that corresponds this one here. So that's another example. And if you look at a really complicated case, so I'm trying to explain it. Hopefully I can make it clear. Okay, so why this is complicated? Because you have the ARIMA differences. At the same time, you have the seasonal differences. So I'm not going to put them into one equation. I'm going to do it step by step. So first step, okay, think this is your original data, xt. The first step is that I got the ARIMA difference, okay? So that's xt minus 1. So this corresponds to the 1 here. And then I take this yt, I do a seasonal difference. So that's yt minus 12. I got another intermediate variable zt, that's the one here. And then I model this zt, okay? So on the left-hand side, I have my zt, and then look at here. I have a MA part. So that's the MA part. At the same time, I have a seasonal MA part. So that's, sorry, this delta should be removed. You also have this delta, epsilon t minus 12, that's the seasonal MA part. Okay, so when you see this kind of very complicated notations, I'm not trying to do it in one single equation. I break it down into 3 steps. Hopefully I'm clear. Okay, so we also have the simulation here, and
this could be potentially
package. There is no simple implementation. So I borrow one example from Rob Heidman's website, and I show you in the studio. So that's how you simulate ARIMA. So this is ARIMA 111, and the seasonal part is 111, and the frequency is quarterly. So that's M equals 4. So you simulate it, and that's how it looks like. And you can plot the ACF. This is non-stationary. That's why the ACF is decaying very slowly. This is the PACF. It looks in this. Okay, so that's the end of my presentation. Thank you very much. I think I overrun the time, but I'm still happy to take questions if you also have time.
Well, thank you very much, Shishwan. I think I put my questions in the Slack.
I think I cannot hear you, Benjamin, so I need to change my. Okay, I simply close my.
Can you hear me now? Shishwan?
Okay, can you say something, Benjamin?
Can you hear me?
I cannot hear you.
Okay, it is strange, but
How to? Can you say something again?
Can you hear me?
Yes, I can hear you now. I think there are some technical issue with my headphone.
Yeah. Okay. So, probably I will start from the last thing I had in mind. So the example you just showed us in seasonal ARIMA, this could potentially be a time series with trend and seasonality. Am I right?
Yes. So the trend.
No, sorry, the equations, the previous one.
Mm-hmm. So the trend.
Because we have two differences in both non-seasonal and seasonal. So can we say that this could be potentially an example when we have both trend and seasonality in our time series?
Yes, my understanding is that is correct, because by doing this difference, you remove the trend.
Yeah. Okay, great.
By this difference, you remove the seasonality.
Yeah.
Mm-hmm.
Great. So another question is, so the question I often get about ARIMA is, when working with real time series, they often have trend and seasonality. So meaning that they're non-stationary. So however, for ARIMA models, the time series must be stationary. So therefore, we need to do these differences or the transformation, as you explained, to make the time series stationary and then fit the model and do the forecasting. So now the question is how the ARIMA model accounts for trend and seasonality in the time series forecasting.
Okay, so my understanding is that, so forget about seasonal ARIMA. Okay, let us focus on the ARIMA. So I think for the ARMA model, this is only for stationary time series. If you have the difference, something like 111 here, this can model non-stationary data. And once you, for example, if your original time series is XC and you do the difference, you go to XC, it is equivalent to use the ARMA 11 here.
Yeah.
So here is the deal. So they are equivalent, just different notations. Whether you want to model original time series by ARIMA 111, or you want to use the first difference time series by ARMA 11. For the seasonal ARIMA is slightly more complicated, and I think it's also the same. If you do those two differences, you got this is the original one, then you do the difference, and then you do the seasonal difference, then you end up with something you can model by ARMA PQ. But this is still equivalent to the original very complex notation.
Yeah. So can we say when we have a trend and then we do the differencing, so and then we do the forecasting. Basically, we forecast the changes between adjacent periods, and that is how actually the trend is accounted for.
Yeah, and when you only focus the difference, but when you want to convert it back to the level or the original cells, you also need to add the difference to the previous cell so that it convert to the level.
Okay. Yeah.
Yeah, for the seasonal arima, yeah, you need a double conversion, I think.
Great. So another thing is, so when selecting the best P and Q, so you explained how we do it with information criteria. So the question is, can we do it based on the out of sample evaluation as well? So you have the training set and test set, or in sample, out of sample, and then you try different P and Q combinations, but with forecasting and out of sample.
I think it depends on the purpose. If it's only for model fitting for the in sample, you use what I presented. But if your purpose is forecasting, so you can calculate the information criteria in out of sample. Sorry, let me put it in this way. So I think you have the I would say training data which you use for model fitting. Then you have the validation period. Then you have the out of sample.
Yeah.
Okay, so instead of what I did, just using the training sample to choose ARMA, you calculated the information criteria for the validation, and then you choose the order for ARMA in the validation period, and then you use whatever you select order to focus out of sample. So in this way, you are still not touching the out of sample data.
Yeah, but can we even in validation, can we, because it is a kind of test set as well, because imagine if you do a rolling origin from the training to validation. And then, so you have the initial training, and then, you add information to this in validation to go to the end of validation. So we do the rolling origin or time series cross validation. So can we use, because imagine I'm interested in minimizing root mean square error, because I want to get the mean of my my forecast right. So can I use the validation and root mean square error, for example, in the validation to get the best P and Q instead of information criteria?
I think that's another criteria to select the order. Yeah, so it's a different criteria. Of course, you can use it, but it does not penalize the number of parameters if you just use MSE or RMSE.
Yeah, exactly. That's right. Okay, Shishwan, the last question for me is, so yeah, you talk about the error term. That is, yeah, normally we assume it's normal distribution, but then it could be a different distribution. So how do you change this in the R function? Can you do it in the ARIMA function you showed us in the R code?
Not in this basic package.
Okay.
So in another package, I forgot the name. I think it's something about a gauge.
Okay.
Maybe it's like it's called a UG gauge or something. So in that package, you can change it into different distributions. I think in the basic package here, it's still normal distribution, but in more advanced packages, they have the functionality of non-normal error setting.
Yeah. Okay, fantastic. I don't think there is any other questions, Shishwan. So that was a fantastic session. Thank you very much. I just stopped the recording now, and